All right, we'll go ahead and get started. Thank you all for coming. My name is Mihir Tandon. I'm a freshman studying computer engineering, and today we're going to talk about world's simplest poker.
Might have to like click the.
Okay, there we go. Uh, okay, so quick disclaimer before we start. Uh, so this presentation is based off of an IML project that I'm currently working on. It's called The Mathematics of Poker-like Games, and it's under Professor Hindelbrand. And that project was actually inspired by a paper by Professor David McAdams of Duke University. It's also titled World's Simplest Poker. So we're still doing some research, so not all the ideas are completely developed. But I might do a short presentation later this semester to like kind of add on to this and like add on ideas that we added, I guess. But and then finally, the point of this talk isn't necessarily to make you a better poker player, but if you can find a way to apply these ideas to your poker games, that would be really cool. So yeah. So okay, so this is a quick outline of what we're going to be doing. So quick introduction, then we'll talk about the cutoff strategy, then some more general strategies. So let's get into it. So poker, is anyone not familiar with poker? Okay, yeah, I think you guys all know what poker is, but today we're going to be considering a very simplified model of poker. So we're going to consider two players, A and B, and they're each dealt a card in the interval 1 through n. So we have n cards from 1 to n, and they're each dealt a card without replacement. So the initial ante in order to play is going to be $1, and then each player can choose to bet an additional dollar or fold, which means they don't bet. And what's important is that they do this independently of the other player's choice. So if one player bets and the other folds, the player who bets wins $1. If both players fold, this is important. The player with the higher card wins $1. And then if both players bet, then the player who has a higher card wins $2. So note that in this case, fold doesn't immediately mean that you lose the hand. So it's not quite like in like real poker, where like if you fold, that means that you're just out of the hand. Because if both players fold, the player who has the higher card wins. Any questions about how the game works? Cool. Oh yeah.
It seems like the amount of money you have would only go down.
So the way it works is that like if I like put in $1 and then my opponent also puts in $1, right? Um, you would actually like win like $2, but your profit is $1. So I should have specified that. But these are like profits, if that makes sense. So like if you put in $1 and your opponent wins also puts in $1 and you win the pot, you win $2, but your profit is $1, right? So these are profits. Cool. All right. Okay, so let's do an example just so you guys can get the idea. So let's say n is 3 for now. Just we'll consider a simple example, so only 3 cards. This is called ace king queen poker because it's technically poker when you only have ace king and queen. So yeah, very simple level of poker. And let's suppose that the other player will bet if and only if they have a card 2 or 3. So we are essentially assuming the other player has a strategy where they bet if they have 2 or 3. So then let's say that you get the card 1. Should you bet or no? Yes or no, and what why? You can like raise your hand or just say it out loud. Yeah.
If you bet, you're sort of assured to lose, especially if they bet.
Exactly. So the answer is no, because if you do bet, then since they bet on 2 and 3, since you have the card 1, they have to have card 2 or 3. So they will always bet, and if you bet, then you have a lower card than them. You're guaranteed to lose. So that would be bad. Let's say you get a 3. Should you bet? Yeah, yeah.
I'm the ties, by the way. Like five.
Yeah, so the cards are without replacement. So there will be no ties. But that's a great question. So now let's suppose you get a 3. Um, should you bet? Yeah, you should bet because you're guaranteed to win. Now let's suppose you get a 2. Should you bet? It's a little bit trickier of a question. I'm seeing get some mixed responses, yes, no, yes, no. So the answer is actually no. And here's why. So you should bet if and only if your expected profit from betting is greater than or equal to your expected profit from not betting, right? So let's calculate the expected profits. So the way that we found these values here is that okay, so like for the way that we calculated these is that let's say that you bet. So then you have a 1/2 chance of your opponent getting the card one, in which case you'd have a profit of one. But there's also 1/2 chance that your opponent would get the card three, in which case you'd lose two because you and your opponent both bet. And then if you don't bet, then you have a 1/2 chance again that your opponent gets a one and then you win, and then 1/2 chance your opponent gets a three and you lose. So your expected profit is zero. So you actually should not bet because you have a higher expected profit. Any questions? Okay, and then just to reiterate, note that we're considering strategies independently of what the other player does. So even if the other player bets, we're not going to consider that in like our decision. Cool. Okay, so now let's kind of generalize this a bit. So let's define a player's betting set to be a subset of 1 through n, and like we're going to call it S of A or S of B, such that a player will bet on card C if and only if their card is in their betting set. So like, for example, if S of A is the empty set, that means that player A will never bet. This is what card they get. And again, we're going to assume n is 3. So if player A is a betting set of the empty set, what should player B, how should player B bet? Yeah.
Should they bet on the upper half cards?
No.
Wait, could you go back to the rules? Like,
Yeah.
yeah. So the person that bets and the other person folds can win one. So
Yeah,
so they should all.
exactly. You got it.
Absolutely, yes.
So let me just go back. Yeah, so they should always bet because if they always bet, because the other player always folds, they guarantee they'll always win, essentially. Does that make sense? Okay. Oops, okay. So now okay. So let's suppose player A bets on all the cards. How should player B respond? Good thought. Well, let's kind of break this down. This is a tricky problem, actually. So you should always bet on three, and you should never bet on one. And the reason for that is that like you'll always win on three and you'll always lose on one. So that should be pretty self-explanatory. Then the only case is two. And for two, we can do the same approach that we did as before. So if you do bet on two, you have an expected profit of 2 times 1/2 minus 2 times 1/2. Because there's a 1/2 probability that your opponent has a one, there's a 1/2 probability your opponent has a three. So your expected payout is zero. If you don't bet, your expected payout is -1. And the reason for that is if you don't bet, you always lose because your opponent always bets. So because of that, you have a higher expected payout if you do bet. So you should bet on two. So your betting set should be 2, 3. So that is the optimal response to the betting set 1, 2, 3. So now let's go through a couple like game theory fundamentals. These should be fairly quick if you're familiar with them. If not, to be a quick refresher. So a zero-sum game is one that the sum of all the payouts from all the players is equal to 0. So poker is a zero-sum game because if I win like X dollars, you lose X dollars, basically. Then we say that a player has a dominant strategy if it's like the best strategy for that player to use, no matter what the other player does. And then we call a strategy deterministic if it always produces the same outcome for a given input. What that means is that like there's no randomness involved in deciding your strategies. They're always like predetermined. So like so far we've only considered deterministic strategies. And then a Nash equilibrium occurs when neither player can gain a higher expected payout if they change their current strategy. So neither player has an incentive to change their current strategy. That's a Nash equilibrium. Any questions about these?
Could you give an example of Nash equilibrium?
Sure. I guess I can use this. So like, let's say that this is like a more general game. We have like player A and player B. Let's say it's like low, high for some parameters of low and high that we don't really know yet. But let's say that like, let's say it's a zero-sum game and these are the payouts for A. So then let's say like this is 5, this is like 3, this is like 10, this is like 2 or something. Okay, so then a Nash equilibrium would be here. And the reason for that is that if both players are currently operating here, player A doesn't want to switch strategies. Like these are, let's say these are player A strategies, these are player B strategies. Player A wouldn't want to switch strategies because if player A switches, they get a lower payout. Player B doesn't want to switch strategies because although this is a higher number, this means it's a higher number for player A. So it's a lower number for player B because it's a zero-sum game. So this would be a Nash equilibrium. Does that make sense? Cool. Okay, so we can compute the payout matrix. Like this is a payout matrix. It's essentially lists all the different possibilities and computes the expected profit for each of them. So we can essentially simulate the game, which takes O of n squared time because there's n squared like possibilities for hands. And then there's 2 to the n total betting sets for each player. So we can simulate the game in O of 4 to the n squared time. As you can imagine, we haven't been able to do this for very large n, but yeah. So if we do that, we get this table here. So what the way this table works, these are the betting sets for player B, these are the betting sets for player A, and all the entries in this table are like the payouts for player A. And just remember that if you were to negate these values, that would be the payout for player B. So knowing what dominant strategies and Nash equilibria, what would they look like in this table? Like if you were to see a dominant strategy or Nash equilibria, how would you go about looking for one, basically? Yeah.
All entries are non-negative.
Uh sort of, yeah. Basically, like if like there's a certain like column where all of the maxes are like in that column, then that column would be dominant. Or I guess it would be because the columns would be yeah. It would be like that makes sense.
I think the plus column would be dominant.
So it almost is, but you can see that there's like a row, like this row, for example, where it's not the maximum. So there actually aren't any Nash equilibria or dominant strategies in this table. So there are no dominant strategies and Nash equilibria for at least n equals 3, which I thought was kind of interesting. So we'll continue to explore this idea later, but for now we're going to talk about the main strategy that players often use, which is called the cutoff strategy. So what is the cutoff strategy? So it's a deterministic strategy where a player will bet if and only if the card they receive is greater than or equal to a certain cutoff value. So the cutoff values are A sub C for player A and B sub C for player B. I'll call them A and B just to so I don't have to keep saying subscripts. And then they're between 1 and n plus 1. So like if player A had a cutoff value of 1, they would always bet. Because they bet if and only if their card is greater than or equal to their cutoff value. So what would be the betting set of a player using a cutoff strategy of 2? Yeah, 2, 3. Any questions about how the cutoff strategy works before we move on? Okay. So if we just analyze this subset of all possible deterministic strategies, we can find like the like an explicit formula for the expected payout in terms of the cutoff values A, B, and N. So without loss of generality, we're going to assume that player A's cutoff is greater than player B's cutoff. And we'll find a formula for player A's expected payout E sub A. And since this is a zero-sum game, player A's payout is just the opposite of player B's payout. So we can find player B's payout easily. Yeah.
Is it ever optimal, like if I have a cutoff strategy, like 1 to N, like K to N, is it ever optimal for me to switch from like K to N to like K minus 1, skip K, then all the way up to N?
That's a great question. We'll explore that more like later in the presentation. Yeah. So notice that in this log statement, we never considered the case when the cutoffs are equal. So I'll leave that to you guys. What's the expected profit when the cutoffs are equal?
Sure.
Yeah. And why is it 0? Yeah, exactly. By symmetry, basically both players are playing the exact same game with the exact same strategy. So by symmetry, both players have a 0 payoff. Any questions about any of this? Okay. So basically, if we do this analysis, we end up with 6 cases to consider. And the way that the labeling for these cases work is the first player is the player's action. So they either fold first player's action, so player A's action. They either fold or bet. Then the second letter is player B's action. So they also either fold or bet. And then the last letter is the outcome for player A. So they either win or they lose. So you'll notice that we only have 6 of the 8 possibilities here. So what happened to the BFL and FBW cases? Why aren't they possible? Yeah, exactly. Yeah. So if player A bets and player B folds, player A always wins. So it's not possible to have an L. And similarly for FBW. So here's just a quick I just kind of plotted like for n equals 10. If player A's cutoff is 6 and player B's cutoff is 4, I kind of colored the 6 different regions here, and like the lattice points just correspond to all the different possible cases. So like for example, the purple region is the region for where player A folds and player B bets, and player A would always lose that showdown. Okay, so then we can compute the total expected profit as just essentially a weighted average of each of the 6 different cases. So we'll find like the expected value of each case and multiply it by the probability that it occurs. And then in this presentation, just for the sake of time, and I don't want to like bore you guys, we're not going to go through all 6 cases because they're all pretty similar. We'll just go through one case, and you guys should kind of get the idea on how we generalize this to the other 5. Any questions? Okay. So we're going to consider the FFL case. So this case, it happens when the first player folds, or player A folds, player B folds, and player A loses the showdown. So let's first compute the probability that this case occurs. So let's call the cards that players A and B receive C sub A and C sub B. So because we're picking the cards without replacement, there's n times n minus 1 ways to choose C sub A and C sub B. And then because player B folds, there's B sub C minus 1 ways to pick players C sub B, which is player B's card, that's less than player B's cutoff. So just all the values that are less than B sub C. And then since player A loses this hand, we need player A's card to be less than player B's card, which means player A's card has to be less than player B's cutoff as well. So because of that, if we already picked 1 card from player B, we have B sub C minus 2 cards left for player A's card. And remember that player A, we assumed at the beginning that player A's cutoff was greater than player B's cutoff. So player A's is still in like their folding region here. So by symmetry, since basically this process is just picking 2 random numbers between 1 and B minus 1, there's a 1/2 probability that player A's card is less than player B's card. So if we put this all together, we can compute the probability this case occurs as just v minus 1 times v minus 2 over 2 times n times n minus 1. So the expected value for this case is -1 because player A will always lose this showdown because that's like how we define the case, and neither player bets. So that's why it's the expected profits for player A is -1. So then if we multiply these together, we get this result for our case, first case. So then we can do all the cases, and then we get this wonderful table here that has the expected profit for player A, as well as the probability each case occurs. So we do have some slightly gnarly expressions, but yeah. So then what we do, as you can imagine, is we go through the algebra of just multiplying this by this, adding it to this times this, etc. for all of the cases. And then if you do that, I thankfully have saved you the time again. We get this formula here. So this formula gives the expected profit of player A given cutoffs like in terms of n and the two cutoff values A and B. So that's great. But remember this formula is only valid if player A's cutoff is greater than player B's cutoff. So we can also compute player B's expected profit as just the opposite of this. And then what we can actually do is, since this game is symmetric, basically we can take this formula and replace every A with a B and every B with an A, right? So if we do that, we can essentially just derive the case when player B's cutoff is greater than player A's cutoff, just by swapping all the variables. So that's like a neat way to just derive that without going through all the cases again. So yeah. So we have a pretty ugly formula for player A's expected profit given the cutoffs A, B, and N. Any questions?
Probably gonna answer this in the next slides, but just as like trend positive for like how does
Yeah.
this function trend?
So here's a quick graph of it. So like this is like player A low high cutoff and player B low high cutoff. And so it's kind of like a like 3D sort of shape. And then like one thing you'll notice is that if player A has a really low cutoff and player B has a really high cutoff, that's really good for player A. Because player A will just keep betting on everything and keep winning. So that's why there's like a really high peak here. And then this can be pretty difficult to visualize. So what I've also done is plotted some level curves. So what level curves are is I fixed essentially I fixed player B's cutoff, and I plotted player A's cutoff as a function of their expected payout. So the darker values indicate larger values of player B's cutoff. So you'll notice like player B has a really high cutoff. It's optimal for player A to choose 1 as their cutoff value. But that's not always the case. If you can make out this main line here, then that's like somewhere over here. So it's not always 1, but it is 1 for a decent number of player B cutoffs. So now, like I kind of alluded to this, we're going to try and just maximize this function. So we're going to maximize player A's cutoff for over like sorry. We're going to maximize player A's expected profit over player A's cutoff, fixing player B's cutoff and N. So for now, let's suppose that player A chooses a strategy such that player A's cutoff is greater than player B's cutoff. So then we can just use the formula that we already derived for the expected profit of player A. And then let's just rewrite this as a quadratic, because these are all really just constants. So this is basically just like a quadratic. So it's not too difficult to maximize, as we see that it has a negative leading coefficient. So it's opening down. And I just took the derivative, although you can also just plug in like negative this over that, or 2 times that. And then you can I just like took the derivative and then set it equal to 0. And that also works, of course. And then, so if we just set it equal to 0 and then solve for player A's cutoff, we find an optimal value for player A's cutoff is 2 plus n plus 3 times player B's cutoff over 4. So we can verify that this value is always between player B's cutoff and player n plus 1. So remember that a cutoff value isn't valid if it's greater than n plus 1. And then we also assume that player A's cutoff was greater than player B's cutoff in this case. So you can show that it does indeed satisfy these bounds over all possible values of player B's cutoff. So this choice is valid. However, there is one issue. Anyone see an issue with this? Sorry? Yeah. The problem is, and this expression is not guaranteed to be an integer. So this won't actually always be the best value because we can't choose a non-integer cutoff. So the way we can fix this is use this slightly strange notation that I'm not even sure is correct, but we're gonna go with it. We have a mix between floor and ceiling for the closest integer function. So an optimal value of player A's cutoff is just given by the closest integer to this expression. So now let's look at the case when player A chooses a strategy less than player B's cutoff. So we'll just use the same formula as before. But notice now we have a parabola that's opening up and not opening down. So we consider the endpoints, which are between 1 and B minus 1, because their cutoff is less than player B's cutoff. So if we first plug in 1, we just get this expression here. And then if we plug in B minus 1 into the expression, we get this gnarly thing. But then it actually simplifies pretty nicely to this, surprisingly. But you'll notice that since player B's cutoff is less than or equal to n plus 1, player A's expected payout is always less than or equal to 0 in this case. So there's really no reason for player A to ever think about using this strategy, as they can get at least as good just copying player B's strategy. So yeah. So in the end, we've essentially shown that an optimal value for player A's cutoff is either 1 or the closest integer to 2 plus n plus 3b over 4, depending on which gives a larger value for the expected payout. Now we could plug these back in and figure out which is like best. However, it's a little bit annoying to do because we have this closest integer function. But in general, as you guys kind of saw from the level curves, player A should use a cutoff of 1 while player B's cutoff is high, and then eventually switch to 2 plus n plus 3b over 4, the closest integer to that, when player B's cutoff gets low enough. So like I said, finding the exact value is a little bit annoying of that switch. So instead, we're gonna kind of use this interesting approximation to kind of drop this closest integer function. So what we're gonna do is kind of make a continuous analog of this problem. So like as n grows large, we can ignore all of the discrete differences between the cards, and then also the fact that the cards are drawn without replacement, and then like everything else like with the closest integer function, of course. So remember that n is not necessarily like the number of cards in the game, but the number of possible hands in the game. So if we were playing like Texas Hold'em with like a 52 card deck, this would be about like 52 choose 2, maybe a little bit less than that because like some hands are equivalent, but that's still like pretty large. And like for the purposes of this game, I'll consider anything greater than like 100 pretty large. So I'll take that. So now we're going to reframe our problem as follows. So we're going to choose cutoffs alpha and beta such that alpha and beta are real numbers in the interval 0, 1. And the cards are randomly chosen real numbers in the interval 0, 1. So we're essentially like taking our whole problem from 1 to n and just compressing it down into 0, 1. And then we can derive continuous versions of our formulas by making some approximations. So player B's cutoff is going to be about n times beta. And the player A's cutoff is going to be about n times alpha, which kind of makes sense because in the discrete version, the cutoffs range between 1 and n. So if we squish this between 0 and 1, it's about beta is b is about n beta if we take n large enough. So now what we can do is substitute these expressions into our formula for our expected profit. And we can derive a new expression for expected profit that's not in terms of n, but essentially considers the limit as n goes to infinity. So when we plug these back in and take the limit as n goes to infinity, we only care about the quadratic terms in the numerator. So we end up with this expression here for the expected profit for beta is greater than alpha, which is just b is greater than a. And then in the case alpha is greater than beta, it's essentially the same thing as before. Any questions? Okay. So now let's maximize, use these new versions to have an easier time maximizing. So we can essentially reuse our a star c as alpha star c values by just taking the limit as n goes to infinity and then like stuffing it into 0, 1, basically. So a cutoff value of 1 in the continuous case corresponds to a cutoff value of 0. Because a cutoff value of 1 is like the lowest possible cutoff, and 0 is the lowest possible cutoff in the continuous case. And then similarly, a cutoff value of 2 plus n plus 3b over 4, the closest integer to that, is going to be about 3 beta plus 1 over 4. And you can just derive that just by like substituting b is about n beta, taking the limit as n goes to infinity, and compressing in 0, 1. So now we have some new optimal values for alpha. And we can plug these back into our expected profit function. And if we do, we get, if we plug in 0, we get 2 beta squared minus beta if alpha chooses a strategy less than beta. And then if we plug in 3 beta plus 1 over 4, we get beta minus 120 squared over 8 if player A chooses a strategy greater than player B's cutoff. So now we can deal with these continuous versions a lot easier. So now we're able to figure out which one is more optimal. So we can just like solve for when the expected profit of choosing 0 is better than the expected profit of choosing 3 beta plus 1 over 4, which just boils down to solving this quadratic here. And if we do that, we find that it is when player B's cutoff is greater than this value here, 3 plus 2 root 6 over 15, which is about 0.5266. So what this means is that player A should choose a cutoff strategy, alpha is 0, or like the lowest possible betting strategy, which again, this is a reminder, is equivalent to betting on everything. If and only if beta c is greater than this 3 plus 2 root 6 over 15. Otherwise, player A should choose a cutoff of 3 beta plus 1 over 4. And what we'll find is that player B's best strategy is essentially to minimize the maximum between these two strategies. So if player B does that, they will achieve their best result by choosing this optimal value here, which I call beta star c, which is just a 3 plus 2 root 6 over 15. But since player A essentially can play to player B strategy, player A gets a positive expected profit of about 0.028. So yeah, player A does come out on top if they essentially can choose their best response to player B strategy, which should be what we predict. And then here's a graph of like the continuous analog, so you can kind of see it. It's basically just like the discrete version, except now it's just like a smooth curve. So any questions just about the cutoff strategy and how we maximized it and anything like that? Okay, yeah.
So A chooses 0 when B chooses exactly 3 plus. Yeah.
Yeah, so if B chooses exactly this, it actually doesn't matter what A chooses because both have the same profit. Like this is the cutoff value for when both are the same. All right, so now we're going to talk a little bit more about general strategies. So far we've just talked, we've gone into great detail analyzing this cutoff strategy and finding like the expected profits. But an important question is this strategy dominant? And what I mean by that is like, can you always maximize your expected payout just using cutoff strategies? So what do you guys think? Yes or no? Like, regardless of what the other player does. Okay, good guess. So let's consider this example. So remember that we're going back to the idea of betting sets. So this means that player B only bets on 3. So let's figure out what player A's optimal response is. In order to do that, I gave you this table again. So if player B chooses a strategy, and just remember that these are player B strategies, and those are player A strategies. So what is player A's best response? Yeah, 1 or 1-3. But neither of those are actually cutoff strategies. So this is a counterexample. And it follows that playing cutoff strategies are not actually optimal. And there are situations where other strategies are better. And it's really interesting if you think about it. Like the best counter to player only betting on 3 is only betting on 1. But yeah. So this being said, it is true that for most strategies that player B can do, and by most I mean like over 90% of all the betting set strategies, it is true that should be cut off. Sorry, there should be betting sets, not bluffing sets. But it can be shown that like cutoff strategies are generally good, basically. But now let's consider another scenario, which I think is best shown with an example. So let's suppose that player A picks some strategy, some betting set S of A. Then player B picks their best optimal response S of B. Then let's say player B is like, or player A is like, player B is choosing this betting set. I should change my strategy so that I pick my maximal response or my best response to S of B essentially. So player A changes their strategy to some new strategy. And then player B is like, hey, I want to change my strategy so I can maximize my payout given player A strategy. So now player B changes their strategy and we get this cycle essentially. So this leads to a sequence of iterated strategies, which I'm just going to call S of I. And what's important to note is that because we only have finitely many possible strategies, and each strategy, like each term in this sequence, only depends on the previous term. There can only be, like this sequence must eventually be periodic. Because there's only finitely many possibilities, and each term only depends on the previous. So we'll say that the period of such a strategy cycle, we'll call that T. So yeah. So here's a question. What other term that we've talked about already refers to a strategy cycle of length 1? Nice. Yeah, it's a Nash equilibrium. Because a strategy cycle of length 1 essentially means neither player wants to deviate from their current strategy. So they always stay at the, like, both using the same strategy. That's a Nash equilibrium. So let's do an example. Let's suppose that n is 3. Again, we're pretty much only going to use examples with n is 3 because otherwise it gets very long. But let's say initially player B only bets on 2 and 3. So here's the wonderful table again. What would player A's best response be? Yeah. Player A should bet on 3. So we'll end up at this cell right here. So then now, given that, player B is going to change their strategy. What do they pick now?
2 or 2.
Yes, that's zeros, maybe. No, one.
Yeah, 1 or 1, 3. Because now we're looking at this column here. Because player A strategy is fixed at 3, and player B strategy is just one of those columns, but 1 or 1, 3 both work. It turns out it actually doesn't matter which one you pick. You can see that shortly, but we'll just assume they use 1, 3. So then, if we continue this process until we end up back to where we started. So what cell comes next? Yeah. Player A is going to shift depending on 1, 2, 3. And then now player B changes to what? Yeah. And then now what happens? Yeah. So then back to here, and then we get a cycle. So the cycle now repeats, and the period is 4. Because we have 4 different elements in the cycle. So this is like the idea of the repeated iterations of optimal strategy. So through some simulations, right now we know that there are cycles of length 4 for all n is less than or equal to 10. You can guess why we haven't checked n is greater than 10. But there are actually also cycles of length 10 for all n greater than, well, between 4 and 10. I should have changed that, but yeah. However, we've yet to prove that these are the only ones. But what's important is that we still haven't found cycles of length 1. And right now we're pretty sure they don't exist. However, we have not proven that, of course. So one thing that I wanted to talk about as well is bluffing. So bluffing is in our poker model a non-deterministic strategy. So the way that bluffing works in our model is that suppose a player if they have a card C and a certain betting cutoff A and bluffing probability P. They will bet with probability P if they have a cutoff, if they have a card less than their cutoff, and then they will always bet if they have a card greater than or equal to their cutoff. So it's basically the same as a cutoff strategy, except you also bet with probability P for values beneath your cutoff. So you can think of that like as a bluff. So currently in our work, we haven't looked too much into bluffing strategies. However, you know from David McAdams from the paper that there is, in fact, if you consider non-deterministic strategies, a Nash equilibrium at 1/3, 1/2, where in the continuous case. So like if we assume a continuous model, and both players will choose the same strategy of bluffing probability 1/3 and betting cutoff 1/4. And then here's just some future work that we hope to do. So one key question that we still haven't answered is that what is the best possible like response betting set? If I like give you a betting set S of B, what is player A's best possible response? Like we've figured it out like computationally for small n, but we don't have like a general like procedure or like formula yet. Also, another question is there a Nash equilibrium if we consider deterministic strategies? So that's equivalent to cycles of length 1 that we were talking about before. Right now we think the answer is no. We know it's no for n is less than or equal to 10. However, we don't know for sure yet. And then also, are there any Nash equilibria or dominant strategies when we introduce bluffing?
I want to ask, why wouldn't like this feels similar to like rock paper scissors?
Yeah.
The optimal strategy is just 1/3, 1/3, 1/3. Is there a similar thing, just like betting with something like bluffing with some probability P overall with 0, 1? Like, is that not a Nash equilibrium?
That's a good question. We haven't looked into that yet. That's definitely something we'll consider though.
If it works out.
Yeah. Yeah, that would correspond to like a cutoff value of like 1.
Yeah.
And then like yeah, we'll never look into that. And yeah, so we'll definitely look more into bluffing and see if there are any Nash equilibria or dominant strategies. And yeah, any questions about or okay. I might come back to this, but for now, are there any questions that you guys are you guys have?
Yeah, that's easy.
Yeah,
I've got for like 10 less than 10 during this cycle, but you know, after you was they got her.
yeah. 10 took like a minute. Well, yeah, because it's like, because, okay, so the whole thing is like a 2 to the 10 by 2 to the n 10 table, right? So you already have like a million entries. Okay, and we're using Python, so
So
that's why. Sorry? Yeah.
Real quick,
Alright,
yeah.
Like how about MATLAB? So
we might look into doing that for, but like the problem is like it's just exponential. So like,
Yeah.
at a certain point, it doesn't like it's not so helpful, you know. But do you guys want to see the Python code?
No.
No. All right. Fair. All right.
wait, I'll joke.
Sorry.
I was joking.
Tell us a joke. What?
I was joking. I want to see it.
Oh, you don't want to see it?
Yeah, I do.
Okay, okay. I'll show it quickly. Right, okay. So I'll just show the wait. Okay, so this is the thing that generates the whole table. So this is like for n equals 4, right? So all I'm doing is I have like the payouts and then like we loop through all possible like cutoff values and then like we loop through all possible subsets of all cutoffs basically. Or I should and then we just like simulate the game and then just add it to the answer basically. So then we just generate this whole table. So this is like the table for n equals 4 and it's already like pretty big. It's 16 by 16.
Are there any symmetries other than like diagonal symmetry? It's really.
Yeah, that's a good question. So far, I think that's really the only thing we found so far. Yeah, that's a great point. You'll notice that because if both players use the same strategy, their payoff is 0. So we have zeros on all the diagonal, and then also like if you reflect over this main diagonal, you just get the negation of your previous value. Yeah.
Have you looked at learning values? So like, because maybe you're more likely to buff when you're like it's 2 instead of 1.
That's a great question. We will look into that. We have not yet.
What if there's like some different type of probability distribution for like on which values? Yeah.
Yeah, no, that's definitely interesting. That would be really cool. It would take some time. I don't know how we would enforce that, but we can do it or try to calculate it. It's probably possible, but we'll look into that.
Like say if you have like an exponential distribution. Yeah, like around some value. That like say 7 is my favorite number and like I wouldn't bet that comes from 7.
Interesting.
Yeah, that would be interesting. Okay, so I do have a brain teaser, but it's more of a just like a problem. Wait. We're just gonna speed through the presentation. Okay, well, any other questions? Yeah.
What happens if you don't know the other your strat, try to change your strat and they don't rotate?
That's a good question. In that case, you would probably assume that they would play like their maximum strategy, and then you would like essentially like they would play their strategy that well it's like kind of hard because there's like a lot of things that the other player can do. So yeah, we haven't looked into that much yet just because like there's so many different possibilities for the other player to do. But yeah, I don't know.
I guess that's probably bad.
But
Hard.
yeah. It's all right, so this is the brain teaser. If you guys want to try it, more of just like a math problem, but no.
Anything to do with poker? Is there a strategy to this game?
Strategy is to solve it.
It's a good one.
Do silent teams.
The side links don't have to be anything, just solve it. The only condition is the angles have to be.
Yeah.
Yeah, it doesn't matter. It's just.
I mean, that's why you know, you put 2025.
Yeah.
So they do every map. So it's a-
So you just want angles that are greater than 91. And it's just, so say if you have like XYZ, that XYZ equals Z,
It's like the thing
then
you choose
you want like all the triple X's.
Wait, let's not spoil that.
Yeah, you can just work out, yeah. Okay, what, we might post this in the Discord and you guys can like DM me your answer or something. Yeah. But, that's all I have, so, thank you guys for being a great audience. Bravo. Thanks.
Yeah, thank you for doing this.
Yeah,
This
no
has
problem.
been very fun.